In this video, I'd like to revisit the geometric picture of the SVD. We had this circle right here, like that, and after multiplication with any matrix A, we have this ellipse, and this ellipse might have this angle. So this is y1, and this might be, let's say, y2, and here we might have x1 in this direction and x2 in this direction, like that. Those are perpendicular and those are perpendicular, and those are the eigenvectors of the covariance matrix of the data points after the transformation. We have also seen that the matrix A is equal to U sigma V transpose, and so A multiplied by xi is equal to U sigma V transpose multiplied by xi, which is equal to yi. Here we can actually note something. Those x1 and x2 are actually v1 and v2, the vectors from the row space of our matrix A. Why? Because if you rotate those vectors using this rotation matrix right here, you will get the original I cap and j cap directions. Right? Because the matrix V itself, which is equal to V1 and V2, will rotate all your space such that I cap will correspond to V1, the first unit vector, and j cap will correspond to the second unit vector, V2. So V transpose, which is the inverse of this, which is equal to V1 transpose, and V2 transpose will do the opposite rotation. It will transform V1 into I cap and V2 into j cap. So those vectors x1 and x2 are actually the perpendicular bases for the row space of the matrix. Similarly, those y1 and y2 are actually u1 right here and u2 right here. Because after you do the first rotation, you do some scaling by the amount of sigma 1 here and sigma 2 here, then you rotate back using this matrix U. This matrix U will transform the unit vector I cap into U1 and the unit vector j cap into U2. So this is the more accurate version of the geometric interpretation of the SVD. Those are the vectors from the row space and those are the vectors from the column space of the matrix A, assuming that the matrix A is an invertible matrix. We also can think of this in a slightly different way. If you multiply this V transpose by any vector x, so V transpose multiplied by vector x is equal to V1 transposed x and V2 transposed x. This actually means that we are getting the component of any arbitrary vector x, like that, in the direction of V1 cap and in the direction of V2 cap. We know that any vector x can be represented as some component in I cap plus some other component in j cap direction. Also, any vector x can be represented as V1 transpose x in the direction of V1 plus V2 transpose x in the direction of V2 cap. But V itself is a unit vector, so we don't need this cap right here. And so this multiplication right here can be thought of as representing any vector x using the V1 and V2 bases instead of the original I cap and j cap bases. We have done something very similar when we were dealing with the BCA. So here we are representing some point x using some bases for the row space. This means that for the diagonalization picture of the SVD, if we have AX is equal to y, which is equal to U sigma V transpose x, we have seen that this can be rearranged to be U transpose y is equal to sigma V transpose x, just like that. So this means the following. If we have any two vectors x and y represented originally in the standard basis, in the I and j standard basis, just like that, then if we represent x using the basis of the row space and also represent y in the basis of the column space of our matrix A, then the relation between the components after multiplication by the matrix A will be just a scaling relation between the corresponding components. Let's have a deeper look at this. Suppose that you have a vector q such that q is equal to some component in the v1 direction plus some other component in the v2 direction. Now, if you multiply a by this vector q1, you will get a A V1 plus B A V2. But this is equal to A sigma 1 U1 plus B sigma 2 U2. So if we multiply a vector Q represented using the basis for the row space of the matrix A, we get another vector represented in the column basis of the matrix A. We can look at the vector Q as follows. Q is some vector represented using the basis for the row space. So Q has two components. The first component can be described as V transpose X of 0, because V transpose X is a vector represented in the row space basis of the matrix A, and here I am getting the first element of this vector. Now the second component right here can be written as V transpose X of 1. I am here using array notation from programming, but I'm not saying anything new. I'm just saying that if you have some vector x, in order to represent this vector x using the basis of the matrix V, then V transpose x will give you this representation you want. So Q is equal to V transpose x. Now this V transpose x has two components. The first component I write it as V transpose x of 0, and the second component I write it as V transpose x of 1. So that's just as simple as that. Now this Q is equal to this. It's equal to A and B. This is the component in V1 direction, and this is the component in V2 direction. Now we found out the following. If we multiply A by this vector Q1, we will get something that is described using the basis of the column space U1 and U2. So those can be described as U transpose Y of 0 and U transpose Y of 1, where we have the x vector represented in the standard ij basis, and also the vector y right here represented in the standard ij basis. Now this first component is equal to A sigma 1, and the second component is equal to B sigma 2. Now this first one right here is equal to V transpose x as a vector, and this right here is equal to U transpose y as a vector, but this is also equal to, here I can have sigma 1, 0, 0, sigma 2 multiplied by AB. But this AB right here is this V transpose X. So we have reached the conclusion that U transpose Y is equal to sigma multiplied by V transpose X, which is actually this original equation right here, but derived using a slightly different way. If you couldn't completely understand this, don't worry, I only need you to understand that those right here will be V1 and V2, the basis for the row space, and those right here will be U1 and U2, the basis of the column space. In the next video, we will think about the situation when the matrix is both square and singular.